Okay, so what I'd like to do to start off today is to return to the section on total differentials and the small increments formula. I might have gone through this a little bit swiftly the last time. I'd like to return to this and just have a look at another example. And I've got an in-class exercise which we'll try together in a few moments as well. Okay, so the small increments formula is a formula that tells us how the change in value of a function is approximated by a nice, meaningful linear combination of the changes in values of any of the variables it depends on, and where the coefficients in that linear combination are exactly the various partial derivatives of the function. Okay? So looking at it in its simplest format in equation 156, so this is equation 156 on page 9. Here we see the situation for a function f of two variables that depends on, two variables, x and y. So what this well, I won't call it an equation, it's an approximation. What this approximation is telling us is that delta f, okay, so that triangle is the capital Greek letter delta, just often used to denote changes in quantities. So delta f here represents the change in value that the function undergoes when its variables x and y undergo changes delta x and delta y. Okay? So the approximation tells us that the change in value of the function is approximately this linear combination of the changes in x and the change in y. And the coefficients of the linear combination, the things multiplying the delta x and the delta y, are the appropriate partial derivative of the function. Okay? If you were using this to approximate the change in value of f between some starting values of x and y and then their new changed values, then these partial derivatives would be evaluated at the starting values. Okay? So they would give you the numerical linear coefficients there that approximate the change in value that the function undergoes when when delta x and delta y change by these events. So that's known as the small increments formula. Small increments being the delta x and the delta y. And it's only an approximation, but the idea would be that for small changes, delta x and delta y, the approximation you'd expect it to be good. Okay? And the smaller the changes are, the better and better the approximation that it would provide. Okay? And it's a linear approximation in the changes delta x and delta y. It generalizes when your function depends on more than two variables, it generalizes in the obvious way. Okay? So the generalization is described in 158. And here we've got the function f depending on n variables, x1 through xn. Okay, n different variables. And there, the change in value of the function is approximately the linear combination of the individual changes. Those are the delta xi. And the coefficients are the corresponding partial, the associated partial derivative of the function with respect to the ith variable, multiplying delta xi. Okay then, so last time we talked through the example concerning the simple pendulum, where the simple pendulum, which is illustrated here, so a mass at the end of a string or rod that's swinging back and forth. And in the ideal case anyway, the idealized simple pendulum, which would be swinging without any friction and in a vacuum, so there's no frictional forces slowing the thing down, it just constantly swings back and forwards under the influence of gravity. And associated to that is this equation of motion, which tells us, well, the way it's presented here, it's telling us how the acceleration due to gravity that's driving the pendulum is given approximately by this expression here, which is this constant 4 pi squared times L over t squared, where L is the length of the pendulum, the length of the string supporting the mass, so to speak, and t is the time period taken for one complete swing. Okay, so starting at its furthest point at the right swinging over to the opposite side, and then returning to finish the complete swing when it returns to its starting. Okay, t would be the time taken for one of those. Okay, that equation comes out of the physics of analyzing, from Newton's laws and so on, and analyzing how this thing moves. But what was going on with this example is imagining the experiment that takes place to estimate what the precise value of the gravitational acceleration constant is here on Earth, so to speak, or wherever this pendulum is located. Okay, so you can set the pendulum swinging, and for a number of complete swings, time how long they take, and then from then you'll be able to get a value of the time period t. You can use a ruler to measure the length of the pendulum. But if you want to do things carefully, scientifically, we accept that these measurements have natural errors associated to them. Okay, so we can never measure things precisely. Okay, which takes on a very deep meaning when you look at quantum mechanics and stuff. You really can't measure things precisely all the time. But at least in the practical macro world, you can't do things exactly. Everything has some kind of associated level of uncertainty to it when you're trying to gauge the length of something or when you're trying to time how long something happens. Okay, so we assume that this length that was measured at 2 meters, but it might be plus or minus 2. What are these? Those are millimeters, 0.002 of a meter. So, we accept it could be anything between 2 meters, 2 millimeters to 2 millimeters less than 2 meters. And similarly, we take that the time period for one complete swing is 2.84 seconds, but plus or minus some kind of error of 100th of a second. And by applying the small increments formula to this, we can work out, well, if those are the errors associated to the measurements of L and T, what would be the associated error we should attach to our prediction for G, or our estimate of G. So feeding the values 2 and 2.84 into the formula just gives an approximation for G of 9.79 meters per second. And then these errors, these maximum errors on the length and time, well, these become upper bounds for the quantities delta L and delta T. Okay? So the actual error made is unknown to us. I mean, we did the best we could and measured it at 2 meters and 2.84 seconds. But what the actual precise values of the errors are is we can't access. Okay? But from our measuring techniques, we have perhaps some upper bounds that we believe in on the worst case that the errors can be. And then applying the small increments formula and basically applying the triangle inequality lets us work out some kind of associated error for the estimate of G. So we applied the small increments approximation. So delta G is approximately this combination of delta L and delta T, where the coefficients are the two partial derivatives. And we work out the partial derivatives coming from this formula for G in terms of L and T. The partial derivative with respect to L is 4 pi squared over T squared. Partial derivative with respect to T, well, because the T is in the denominator in T squared, you got minus 1 over T cubed times 2, so the 4 became an 8. So you got minus 8 pi squared L over T cubed. But then we applied the triangle inequality, so the absolute value of the sum of these two quantities is less than or equal to the sum of the absolute values. We don't need absolute value signs around L or T because those are positive quantities, a length and a time measurement. Okay, but the absolute value signs remain over delta L and delta T, which would be the actual errors in measurement that were made at the beginning. Okay. But we have upper bounds for those of 0.002 and 0.01 respectively. So feeding them in there gives an overall upper bound of 0.079 for our estimate, for the change, delta G, the precise error we've made in estimating the value of G. So there's some unknown error that we've made in estimating G with this estimate of 9.79, but at least now we have this, we know something about the possible error that we've made through the small, with the help of the small increments formula. Okay? So we'd attach a natural error bound or prediction error to our estimate for G of 0.079 meters per second. Okay, so that's one application of it. The second one is to looking at the resistance to the flow of electrical current put up by a length of wire. So here we've got a length of wire, which we think of as a cylinder. It has a certain length and a certain cross-sectional area, certain thickness to the wire. Okay, the cross-section of the wire, think of as a disc, and the wire is thick, it's a large disc. If the wire is small, the wire is thin, it's a very small disc. Okay. Now, from the theory of electronics, we get this relation here about how the resistance to the flow of electrical current put up by that length of wire, how it depends on those two characteristics, on the length and the cross-sectional area. So it has this nice relation that the resistance is just linearly related to the quantity L over A. Okay, so if the length of the wire gets longer, the resistance is going to increase. Okay, it's harder and harder for the electricity to flow through the wire the longer it is. But if the cross-sectional area increases, well, that increases the denominator here, so that decreases the resistance. In a very kind of woolly, naive intuition, the thicker the wire is, the easier it is for the electricity to flow through. There's more room for the electricity to move around within the wire. It's not the correct technical interpretation, I'm sure, but it makes kind of sense. And there's also this parameter here, which is rho, which is the Greek letter rho, the equivalent of R. That's called the resistivity. So that's something attached to the particular material. Okay, so copper, for instance, is a good conductor. That would have a low resistivity, but something like different kinds of metals would have higher resistivity than copper, or something like plastic would have an extremely high resistivity. Okay, so the resistivity rho is some measurement or something attached to some property of the material that makes up the wire, and so obviously that affects the resistance. But then the length and the area affects it like that. So what we're going to apply the small increments formula here. Well, in this situation, what we're imagining is, well, suppose that the area, the cross-sectional area of the wire decreases by 1%, and suppose the length of the piece of wire were increased by 2.5%. What would be the resulting change in the wire? Now, if you think about it, both things are going to make the resistance greater. If the length increases, it's going to increase the resistance. If the cross-sectional area decreases, if the denominator gets smaller, that's also going to increase R. We can tell that just from the positions of L and A in the numerator and the denominator, respectively. But the question is, one of them is decreasing by 1%, the other one by 2.5%. Is there a way we can nicely understand what the combined change into the resistance will be? Well, that can be done. I mean, there are many ways to do that, but one nice way to do it is to apply the small increments formula. So applying it to that equation, so R depends on L and A, so the change in R will be approximately this linear combination of the changes in L and A, delta L and delta A. Now we're talking here about percentage changes. We were told that the length increases by 2.5%. So the actual change in value of the length will be 0.025 times L, times its current length. Okay. The length, we're told, is increasing by 2.5%. So what's the actual change? Delta L in the length, it's going to be an increase, so this positive multiple of its current length. So 0.025, that's your 2.5%. Times L. And for the cross-sectional area, the information says that decreases by 1%. So the change, delta A, is a negative quantity because it's decreasing, and its change is 1% of its current value, 0.01 times A. The other quantities, delta R and delta dRdL and dRdA, the two partial derivatives we can obtain from the formula rho L over A, differentiate them. So dRdL is rho over A, and dRdA is going to be minus rho L over A squared. So the double minus sign there combines to give you the plus. So we can work out those two partial derivatives. And because we get these extra factors here, L and A, remember these are percentage changes, so we get these extra factors of L and A here in the delta L and delta A, you actually see the return of the quantity R. So we got rho L over A and rho L over, well, over A squared, but also multiplied by A. So again, you've got rho L over A. So we got the quantity R here and the quantity R there as well. So you can see how those two percentage changes, 0.025 and the 0.01, they combine here to give us an overall change in delta R of approximately 0.035 R. Okay. So that's a 3.5% increase in the resistance of the wire. Okay, 3.5% because that's the proportion of its current value, its current resistance R, and an increase because it's a positive quantity. Okay, there's no negative sign attached. Okay. So again, this is another slightly different way to apply and interpret and make use of the small increments formula. Okay. Okay, so to give us something to do and to keep ourselves active, I put up here on Moodle just an extra worked example that we can do here in this week's section. So a further small increments formula example. I don't have it on a handout or anything. It's not too long. So it's a similar one to the last one. So I'd like to give you a few minutes now to work through this, see how you get on with this one. So it's a sample question. This might easily be part of an exam question. So here we're talking about the volume of a donut, or of a torus, this kind of shape. So the spatial volume occupied by that. Now this is a torus with circular cross sections. So its core is a circle, and its cross section at each stage is a circle. So there's two parameters that characterize such a torus. That's the inner and outer radii. So the inner radius is the distance from the center, just kind of hovering here in the middle of the torus, to the inner edge. That's this distance r, little r. The outer radius is the distance all the way from the center all the way to the outer edge of the torus, and that's the quantity capital R. This is the inside of the torus here. This is a kind of plan view of it. And the equation for the volume is this nice expression here, pi squared over 4 times the square of the distance times the sum of the radii. But what we're imagining now is that both the radii are increasing by 1%. So to apply the small increments formula and work out an approximation for how the volume is going to change, the two radii both increase by 1%. Okay? So this will be following the treatment given to the resistance of the wire, this time to the volume of the torus. We'll take a few minutes on that to work on it with your neighbors and discuss it and see how you'd approach it. And I'll go through the solutions shortly.
Oh yeah, very traditional being resistant could a small yeah. How much is here? 1%. 1% multiplied and yeah. If I do it, the big R and small R here. And oh no, no, you don't. Then you just put them on your own. Yeah, because that's the change in the. Now, now we need to differentiate we differentiate the we
Well, it's just a constant function. It's just
if you differentiate the over here. Then it's what you get with respect to N. You get is a P over N. Yeah. Because that's where they differentiate this one. Yeah, this one. Oh yeah, that one. Is that right? Yeah, pi over 4. With respect to which one? DR. With respect to the big R, big R. So we get
if you've got two things, you differentiate one times by the other, and add that yeah, that would have been easy.
That's like constant. And then that's production. Like this. Differentiation of this one, no, this one. And so differentiation of this one is 2. I don't think so. Well, you can we expand it or we just differentiate it like it is?
That's up to you. You could do,
Anything.
yeah.
Okay, expand that.
This is just a constant. It is effectively checking, but I have a shortcut. Explain it.
I just want to correct that question from and then just do that right.
It does need
I would say.
The small increments formula here is, T depends on capital R and R. Not two different R. So it's the similar expression as before, linear combination of the changes in capital and lowercase r multiplied by the corresponding partial derivatives.
Now you have to do the other half.
And you put the 0 and 0. Oh,
Work out.
my differentiation is what is differentiation of this one and this one? R? Yeah. Where we are. So I did just differentiate with respect to the big one. Now need to differentiate with respect to the small one.
Where did this you expanding part of think very carefully about why.
So if I want to add them, do I need to delete them out now? What do I need to do? This is my differentiation. Which one? Both of them. Okay. Plus, I've done this one. So why? Why you just put substitute in here? Substitute.
So this should be a minus. Makes it even more.
Okay, I'm seeing some good progress there. I mean, first of all, the changes, both these quantities are increasing by 1%. So the changes in both cases would be 1% of the variable. So the change delta capital R will be 0.01 capital R. And the change delta little r will be 0.01 times little r. If you continue to develop it, you then got to think about the partial derivatives. Some of you are multiplying this thing out. Okay, so it'll multiply out to this cubic polynomial in capital and lowercase r, upper and lowercase r. You can also do the partial derivatives by using the product rule, the chain rule, and keeping keeping that factorization alive in it for as long as possible. You know? Because ultimately, just like in the resistance example, ultimately we want to bring this expression as some proportion of V. So we're looking to express the change in the volume as a percentage change in volume. So our aim or our expectation is this whole quantity will come out to be some proportion of V, some constant multiple of V, and looking at that constant, then we can extract the percentage out. So it might be an idea to maybe not fully expand that into the cubic polynomial, but keep it in that factorized form and do the differentiation using combination of the product and chain rules as appropriate. Would you like a few more minutes at it, or?
I've done my differentiation here, but so I think I need to do the first differentiation, multiply by +0.1. Is that right?
Yeah.
And then the second differentiation is starts from here, multiply by this one.
Yeah. We'll see how it all comes together as a proportion of V. Yeah, first we have to be combined into something.
The part one is the part two is minus 5 over the
Okay, so to look at this, maybe I'll start going through the solution now, just to finish by 10 to.
Because this one is minus.
So if I want to differentiate v with respect to capital R for here, well, I keep pi squared over 4. That's a multiple in it. And then what I see is two brackets depending on capital R, two functions depending on capital R, so I should use the product rule. And if I hold the first one the same, I'll have r minus little r squared. And when I differentiate the second one, well, the derivative of the second bracket with respect to capital R is simply 1. So this gets multiplied by 1. And then continuing the product rule, we'd need a plus. And this time we're holding the second bracket the same and multiplying by the derivative of the first one. So the second bracket gets held the same. It's still r plus little r. And it gets multiplied by the derivative of the second one, which is 2 capital R minus lowercase r. And that's the derivative of the first bracket with respect to capital R. So that's all that quantity, and that gets multiplied by 0.01 capital R. And then we've got the second term, the dv d little r. Again, we've got pi squared over 4 for the derivative of v. Again, applying the product rule. So we hold the first bracket the same, capital R minus little r all squared. And we multiply it by the derivative of the second bracket, which is simply 1. And then we add on the second part of the product rule. So this time we're keeping the second bracket the same. And we multiply by the derivative of the first bracket with respect to little r. So the squaring is on the outside. So here's where we're using the chain rules. Is 2 times capital R minus little r. But it gets multiplied by a minus sign. So let me change this here to a minus sign. And then that gets multiplied by 0.01 little r. So then we've got, kind of a big algebraic kind of mess, so to speak. But all of this, what we'll be looking for here is some kind of multiple of v, because we're hoping to express this as a percentage change in the volume. So this algebraic expression, hopefully we can recombine it as some scalar multiple of v. So everything is a pi squared over 4 in front of it. So I bring that all the way out to the front. That's good, because so does v have that quantity in it.
Usually has that one.
Both quantities have a 0.01 in factor. So actually I can take that out to the front, 0.01 times pi squared over 4. And that's beginning to simplify it down a bit. So when we look inside then, what do we find? We find we've got an r minus little r all squared. That gets multiplied by capital R. And then we've got plus 2 r plus little r minus little r times capital R. That's the contribution from the top line. The contribution from the bottom line is r minus r all squared, but this time multiplied by little r, and then negative 2 r plus r minus r, finally multiplied by little r.
So what's the sign between them? Plus or?
Yeah, plus. So this that plus there, yeah. Okay, so this is looking good. Hopefully we can start to see some things appearing. Okay, if we bring these r minus r squared terms together, factorize those, and it's multiplied by the sum, r plus r. That's good, because that's then part of v. And then what have we got here?
2r plus r minus r.
Yeah. 2 r plus r, and r minus r times again r minus r. So you got r minus little r whole squared. So we see the volume expression starting to recombine. So you look at the formula for volume, the pi squared over 4 times the square of the difference times the sum. So again, we have all that pattern appearing. We've got the square of the difference times the sum in both terms here. So you got
Second part. R plus r minus r squared.
so to get all of this here,
Don't you do r plus r squared?
no, because there's one copy of r plus r in each term, so I factorize that out. Then there's one copy of r minus r,
Okay.
so I factorize that out. But then there's a second copy, which is this capital R minus capital R.
Oh, okay.
So that's where the second factor of r minus r comes from to give you the square on this one. So in total there, we've got 3 times this expression. So we take this factor 3 out, the 1 plus the 2, so you got 0.03 pi squared over 4 times r minus r squared, r plus r, which is 0.03 times v. So that's our percentage, that's our delta v, the change in the volume of this torus expressed as a percentage change in the current.
Where did you get that 0.03?
The 0.03 comes from my 0.01, but taking this factor of 3 out, you got a 1 plus 2 times all of that, so you got 3 times it. So I just multiplied the 3 by the 0.01, and the pi squared over 4 is part of v. Yeah? All this rest here is v. So the conclusion is, with both of the radii increasing by 1%, this leads to a 3% increase in the volume. So the 1% increases in the 2 radii yield approximately a 3% increase in the volume v. Okay, so again, that's an application of how the small increments formula can be used in situations like that. And in the second lecture later today, we'll be introducing some more theoretical material, which is about the multivariable analog of the chain rule. Okay, so the chain rule, which you're familiar with from one variable differential calculus, has a corresponding analog in multivariable calculus. So we'll look at that in the second lecture today, and then I've got a big more in-class problems based on that for the third session today. Okay, so I'll see you later on.